Hello. Welcome to the 7th module of the Python Fundamentals course, where we'll cover comprehensions, iterable objects and iterators, lazy evaluation with generators, and various tools included with Python for working with iterable objects. Comprehensions in Python are a concise syntax for describing lists, sets, or dictionaries in a declarative or functional style. This shorthand is readable and expressive, meaning that comprehensions are very effective at communicating intent to human readers. Some comprehensions almost read like natural language, making them nicely self-documenting. Let's start with list comprehensions. Comprehensions are much easier to demonstrate than they are to explain, so let's bring up a Python REPL. First, we'll create a list of words. Why? Sometimes I've believed as many as 6 impossible things before breakfast, by splitting a string. Now comes the list comprehension. The comprehension is enclosed in square brackets, just like a literal list, but instead of literal elements, it contains a fragment of declarative code which describes how to construct the elements of the list. Here, the new list is formed by binding word to each value in words in turn and evaluating len word to create a new value. The general form of list comprehensions is expression of item for item in iterable. That is, for each item in the iterable object on the right, we evaluate the expression on the left, which is almost always, but not necessarily, in terms of the item, and use that as the next element of this new list. This comprehension is the declarative equivalent of the following imperative code, which uses a for loop and a list to accumulate the lengths found so far. Notice that the source object over which we iterate doesn't need to be a list. It can be any iterable object, such as a tuple. The expression which is in terms of the item can be any Python expression. Here we find the number of decimal digits in each of the first 20 factorials using the range function to generate the source sequence. Note also that the type of object produced by list comprehensions is nothing more or less than a regular list. Sets support a similar comprehension syntax using, as you might expect, curly braces instead of square brackets. Our number of digits in factorials result contain duplicates. By building a set instead, we can eliminate them. Although note that the resulting set is not necessarily stored in a meaningful order, since sets are unordered containers. The third type of comprehension is the dictionary comprehension. This also uses curly braces and is distinguished from the set comprehension by the fact that we now provide 2 colon-separated expressions for the key and value, which will be evaluated in tandem for each item. Here's a dictionary we can play with which maps countries to their capital cities. The UK to London, Brazil to Brasilia, Morocco to Rabat, and Sweden to Stockholm. One nice use for a dictionary comprehension is to invert a dictionary so we can perform efficient lookups in the opposite direction. This example converts from a capital to country mapping into a country to capital mapping. Note that dictionary comprehensions do not usually operate directly on dictionary sources. Well, they can, but recall that iterating over a dictionary yields only the keys. If we want both the keys and the values, we should use the items method of the dictionary and then use tuple unpacking to access the key and values separately. Should your comprehension produce some identical keys, later keys will overwrite earlier keys. In this example, we map the first letters of words to the words themselves, but only the last H word is kept. Remember that there's no limit to the complexity of the expression you can use in any of the comprehensions, but for the sake of your fellow programmers, you should avoid going overboard and extract complex expressions into separate functions to preserve readability. The following is close to the limit of being reasonable for a dictionary comprehension. It uses the standard library glob module to find all of the Python source files in a particular directory, and then creates a mapping from the full path name for those files to the size of the file in bytes. The file path and file size are derived using facilities of the OS module. To make this interesting, we'll first define a primality testing predicate function. This function for identifying prime numbers won't win any prizes for efficiency, but it's reliable, simple to understand, and doesn't use any features of Python we haven't yet encountered. All three types of collection comprehension support an optional filtering clause which allows us to choose which items of the source are evaluated by the expression on the left. We can use our new isPrime function as the filtering clause of a list comprehension to produce all the primes less than 100, with the numbers up to and including 100 being produced by a call to the range constructor. We have a slightly odd looking x for x construct here, because we're not applying any transformation to the filtered values. The expression in terms of x is simply x itself. There's nothing to stop us combining a filtering predicate with a transforming expression. Here's a dictionary comprehension which maps numbers with exactly 3 divisors to a tuple of those divisors. Simple is better than complex. Code is written once, but read over and over. Fewer is clearer. Comprehensions are often more readable than the alternative. However, it's possible to overuse comprehensions. Sometimes a long or complex comprehension may be less readable than the equivalent for loop. There is no hard and fast rule about when one form should be preferred, but be conscientious when writing your code and try to choose the best form for your situation. Above all, your comprehension should ideally be purely functional. That is, they should have no side effects. If you need to create side effects, such as printing to the console during iteration, use another construct, such as a for loop instead. Comprehensions and for loops are the most frequently used language features for performing iteration. That is, taking items one by one from a source and doing something with each in turn. However, both comprehensions and for loops iterate over the whole sequence by default, whereas sometimes more fine-grained control is needed. There are 2 important concepts here on which a great deal of Python language behavior is constructed: iterable objects and iterator objects, both of which are reflected in standard Python protocols. The iterable protocol allows us to pass an iterable object, usually a collection or stream of objects such as a list, to the built-in iter function to get an iterator for the iterable object. Iterator objects support the iterator protocol, which requires that we can pass the iterator object to the built-in next function to fetch the next value from the underlying collection. As usual, a demonstration at the Python REPL will help all these concepts crystallize into something you can work with. We'll use a list of the names of the seasons, in British English no less, as our iterable source object. We ask our iterable object to give us an iterator using the built-in iter function, and then request a value from the iterator using the next function. Each call to next moves the iterator through the sequence, returning spring, summer, autumn, and winter. But what happens when we reach the end? In a spectacular display of Python's liberal attitude to errors, Python raises an exception, specifically of the type stop iteration. Those of you coming from other programming languages with a more straight-laced approach to exceptions may find this mildly outrageous, but I ask you, what could be more exceptional than reaching the end of a collection? It only has one end after all. This attempt at rationalizing the language design decision makes even more sense when one considers that the iterable series may be a potentially infinite stream of data. Reaching the end in that case really would be something to write home about, or indeed raise an exception for. With for loops and comprehensions at our fingertips, the utility of these lower-level iteration protocols may not be obvious. To demonstrate a more concrete use, here's a little utility function which, when passed an iterable object, returns the first item from that series, or, if the series is empty, raises a value error. This works as expected on any iterable object, in this case demonstrated on both a list and a set. It's worth noting that the higher level iteration constructs such as for loops and comprehensions are built directly upon this lower level iteration protocol. Now we come on to generator functions, one of the most powerful and elegant features of the Python programming language. Python generators provide the means for describing iterable series with code in functions. These sequences are evaluated lazily, meaning they only compute the next value on demand. This important property allows them to model infinite sequences of values with no definite end, such as streams of data from a sensor or active log files. By carefully designing our generator functions, we can make generic stream processing elements which can be composed into sophisticated pipelines. Generators are defined by any Python function which uses the yield keyword at least once in its definition. They may also contain the return keyword with no arguments, and just like any other function, there's an implicit return at the end of the definition. To understand what generators do, let's start with a simple example at the Python REPL. We'll define the generator, and then we'll examine how the generator works. Here we write a generator called gen123, which yields successively 1, 2, and 3. The generator function is introduced by def, just as a regular Python function. And as we've seen, we must use the yield keyword at least once within the definition. Here I'm yielding a value of 1, and then 2, and then 3. We'll enter a blank line to complete the definition, and there we are. Now let's call gen123 and assign its return value to g. As you can see, gen123 is called just like any other Python function, but what has it returned? G is a generator object. Generators are in fact Python iterators, so we can use the standard ways of working with iterators to retrieve or yield successive values from the sequence. To retrieve the next value from an iterator, we use the built-in next function, passing the iterator, or generator in this case, to the function. So next g returns 1, and again 2, and again 3. Take note of what happens now that we've yielded the last value from our generator. Subsequent calls to next raise a stop iteration exception, just like any other Python iterator. Because generators are iterators, they can be used in all the usual Python constructs which expect iterators, such as for loops. Here we call the generator again, and in each iteration of the loop we print the returned value. 1, 2, 3, just as we'd expect. Be aware that each call to the generator function returns a new generator object. Here we call gen123 again, assigning to h, and again assigning to I. We can see when we display these objects that they have distinct addresses. This means that each generator can be advanced independently. Let's request the first value from h, the second value from h, and now the first value from I. Let's take a closer look at how, and crucially when, the code in the body of our generator function is executed. To do this, we'll create a slightly more complex generator that traces its execution with good old-fashioned print statements. As we enter the generator, we'll print a message. Then we will yield 2, then print a message about yielding 4, and then yield 4, print a message about yielding 6, and then yield 6. Then at the end of the generator function, we'll print a message indicating that the function is about to return. A blank line to complete the definition, and now we can call our new generator, assigning to g. Note that at this point the generator object has been created and returned, but none of the code within the generator body has yet been executed. Now let's call the built-in next function on our generator. See how when we request the first value, the generator body runs up to and including the first yield statement. The code executes just far enough to literally yield the next value. When we call nextg again, execution of the generator function resumes at the point it left off and continues running until the next yield. And then the final value, the function resumes again until it yields 6. After the final value is returned, the next request causes the generator function to execute until it returns at the end of the function body, which in turn raises the expected stop iteration exception. Now we'll look at how our generator functions, which resume execution each time the next value is requested, can maintain state in local variables. In the process of doing so, our generators will be both more interesting and useful. The resumable nature of generator functions can result in complex control flow, so we'll be watching the execution of these generators in a graphical Python debugger. I'll be using PyCharm, but you can use any Python debugger to trace generator execution. We'll be showing two generators which demonstrate lazy evaluation, which will then combine into a generator pipeline. The first generator we'll look at is called take, which retrieves a specified number of elements from the front of a sequence. Note that the function defines a generator because it contains at least one yield statement. This particular generator also contains a return statement to terminate the stream of yielded values. The generator simply uses a counter to keep track of how many elements have been yielded so far, ending the sequence when we reach a specified count. Since generators are lazy and only produce values on request, we'll drive execution with a for loop in a runTake function. In runTake, we create a source list called items, which we pass to our generator function along with a count of 3. Internally, the for loop will use the iterator protocol to retrieve values from the take generator until it terminates. Once execution begins, the for loop in runTake requests a value from take, which runs until it encounters the yield statement. At this point, control returns to runTake, which prints the value, until we get to the next iteration of what is in effect the outer for loop. Each iteration of the outer loop causes execution to be transferred back into runTake just sufficiently to yield the next value. Eventually, the counter variable is equal to the count argument and will literally return from runTake. Behind the scenes, this raises a stop iteration exception which is caught by the internal machinery of the for loop in runTake. This is the signal that take has done its work, so the for loop exits and the program completes. Now let's bring our second generator into the picture. This generator function, called distinct, eliminates duplicate items by keeping track of which elements it's already seen in a set. In this generator, we also make use of a control flow construct we have not previously seen, the continue keyword. The continue statement finishes the current iteration of the loop and begins the next iteration immediately. When executed in this case, execution will be transferred back to the for statement, but as with break, it can also be used with while loops. In this case, the continue is used to skip any values which have already been yielded. As execution starts, the for loop in runDistinct requests a value from distinct. This runs until it reaches yield, which on this iteration simply returns the first item retrieved by this inner for loop from the items list. Control flow transfers to runDistinct, which prints the value and proceeds with its next iteration. Note how when execution of distinct resumes, we actually complete the work of the previous iteration by remembering the value just yielded before getting on with the most recently requested value. We can do this because item is not reassigned until we get back to the for statement. On the third iteration, the next item retrieved from the source is already present in the seen set. Control enters the if block and the continue statement is executed, transferring control back to the beginning of the innermost loop. Eventually, the items list is exhausted, the generator returns implicitly at the end, the for loop in runDistinct completes, and the program exits. Now we'll arrange both of our generators into a lazy pipeline using take and distinct together to fetch the first 3 unique items from a collection. A coherent verbal description of step-by-step execution of a generator pipeline may not even be possible, but that's not going to stop us trying. When execution starts, distinct must be called first in order to produce the argument for take. Of course, distinct returns the generator object over which take will be iterating. In turn, The generator object returned by take will be iterated over by the for loop in our run pipeline driver function. This part of the process is hidden from the view of the debugger. When the outermost loop in run pipeline requests its first value, execution is transferred to take. Remember, the iterable over which take is looping is the generator produced by distinct. When the for loop in take requests the first value from this generator, control is transferred to distinct. Distinct now runs until it reaches the yield, at which point it is returning the first item from the source list, 3. The value is yielded back to the for loop in take, which executes until it in turn yields the value back to the loop in run pipeline, which only now starts its first iteration, printing the first value. Execution continues in this interleaved manner until the first 3 distinct values have been yielded and printed. The advantage of this approach is that distinct only does just enough work to yield the first 3 distinct values, rather than processing its whole source list. It pays to be lazy. Laziness and the infinite. Generators are lazy, meaning that computation only happens just in time when the next result is requested. This interesting and useful property of generators means that they can be used to model infinite sequences. Since values are only produced as requested by the caller, and since no data structure needs to be built to contain the elements of the sequence, generators can safely be used to produce never-ending or just very large sequences like sensor readings, mathematical sequences such as primes or factorials, or perhaps the contents of multi-terabyte files. The authors of this course are sworn by sacred oath never to use either Fibonacci or Quicksort implementations in demonstrations or exercises. Allow us to present the function for the Lucas series, which has nothing whatsoever to do with the order in which you should watch the episodes of Star Wars. The Lucas series starts with 2 and 1, and each value after that is the sum of the 2 preceding values. So the first few values of the sequence are 2, 1, 3, 4, 7, and 11. The first yield produces the value 2. The function then initializes a and b, which hold the previous 2 values, needed as the function proceeds. Then the function enters an infinite while loop, where first it yields the value of b, and then second, a and b are updated to hold the new previous 2 values, using a neat application of tuple unpacking. Now that we have the Lucas generator, it can be used like any other iterable object. For instance, to print the Lucas numbers, you could use a loop like this. For x in Lucas, print x. Of course, since the Lucas sequence is infinite, this will run forever, printing out values until your computer runs out of memory. Use Ctrl-C to terminate the loop. Generator expressions are a cross between comprehensions and generator functions. They use a similar syntax as comprehensions, but they result in the creation of a generator object, which produces the specified sequence lazily. The syntax for generator expressions is very similar to list comprehensions. Expression of item for item in iterable, delimited by parentheses instead of the brackets used for list comprehensions. Generator expressions are useful for situations where you want the lazy evaluation of generators with the declarative concision of comprehensions. For example, this generator expression yields a list of the first 1 million square numbers. At this point, none of the squares have been created. We've just captured the specification of the sequence into a generator object. We can force evaluation of the generator by using it to create a long list. This list obviously consumes a significant chunk of memory, in this case about 40 megabytes for the list object and the integer objects contained therein. Also notice that a generator object is just an iterator, and once run exhaustively in this way will yield no more items. Repeating the previous statement returns an empty list. Generators are single-use objects. Each time we call a generator function, we create a new generator object. To recreate a generator from a generator expression, we must execute the expression itself once more. Let's raise the stakes by computing the sum of the first 10 million squares using the built-in sum function, which accepts an iterable series of numbers. If we were to use a list comprehension, we could expect this to consume around 400 megabytes of memory. Using a generator expression, memory usage will be insignificant. This produces a result in a second or so and uses almost no memory. Looking carefully, you'll see that in this case we didn't supply separate enclosing parentheses for the generator expression in addition to those needed for the sum function call. This elegant ability to have the parentheses used for the function call also serve for the generator expression aids readability. You can include the second set of parentheses if you wish, but it's not required. As with comprehensions, you can include an if clause at the end of the generator expression. Reusing our admittedly inefficient isPrime predicate, we can determine the sum of those integers from the first 1,000 which are prime, like this. So far we've covered the many ways Python offers for creating iterable objects. Comprehensions, generators, and any object that follows the iterable or iterator protocols can be used for iteration, so it should be clear that iteration is a central feature of Python. Python provides a number of built-in functions for performing common iterator operations. These functions form the core of a sort of vocabulary for working with iterators, and they can be combined to produce powerful statements in very concise, readable code. We've met some of these functions already, including enumerate for producing integer indices and sum for computing summation of numbers. In addition to the built-in functions, the itertools module contains a wealth of useful functions and generators for processing iterable streams of data. We'll start demonstrating these functions by solving the first 1,000 primes problem using the built-in sum function with two generator functions from itertools, islice and count. Earlier we made our own take generator function for lazily retrieving the start of a sequence. We needn't have bothered, however, because islice allows us to perform lazy slicing similar to the built-in list slicing functionality. Once we've imported the itertools module, to get the first 1,000 primes we need to do something like this: itertools.islice all primes 1000. But how to generate all primes? Previously, we've been using range to create the raw sequences of integers to feed into our primality test. But ranges must always be finite, that is, bounded at both ends. What we'd like is an open-ended version of range, and that is exactly what itertools count provides. This returns a special islice object which is iterable. We can convert it to a list using the list constructor. Answering our question about the sum of the first 1,000 primes is now easy, so long as we remember to recreate the generator when we pass it to sum. The answer is 3,682,913. Two other very useful built-ins which facilitate elegant programs are any and all. They're equivalent to the logical operators and and or, but for iterable series of bool values. Any returns true if any of the series it's passed are true, and all returns true if all of the series passed to it are true. Here we use any together with a generator expression to answer the question of whether there are any prime numbers in the range 1328 to 1360 inclusive, and remarkably the answer is false. For a completely different type of problem, we can check that all of these city names are proper nouns with initial uppercase letters. The last built-in we'll look at is zip, which, as its name suggests, gives us a way to synchronize iterations over two iterable series. For example, if we have two columns of temperature data, one from Sunday and one from Monday, we can combine them together into pairs of corresponding readings. We can see that zip yields tuples when iterated. This in turn means we can use it with tuple unpacking in the for loop. In fact, zip can accept any number of iterable arguments. Let's add a third time series and use other built-ins to calculate statistics for corresponding times. Here we use the min and max built-ins for the minimum and maximum temperatures, and the sum and len built-ins to compute the average temperature. Perhaps, though, we'd like one long temperature series for Sunday, Monday and Tuesday, We can then lazily concatenate iterables using itertools chain, so this is different from simply concatenating the three lists into a new list. We can now check that all of those temperatures are above freezing point without the memory impact of data duplication. Before we summarize, we'd like to pull a few pieces of what we've made together and leave your computer computing the Lucas primes. This shows the beautiful composability of generator functions, generator expressions, pure predicate functions, and for loops. When you've seen enough or broken some records, we recommend you spend some time exploring the itertools module.